This is the last section of chapter 3. 3.11 is the summary. This is also an abstract section, and it's the kind of section I think about halfway through chapter 4 you'll start to understand better. So just recognizing that, I've taught this class, I don't know, probably 4 or 5 years, and it's chapter 3 that students really struggle with. In the previous chapters, students will struggle with computations, integration, or what step do I do things in. But chapters 1 and 2, and most of 4 are computational chapters. Solve an equation using separation of variables, take a determinant. Chapter 3 is very conceptual, and it will overshadow chapter 4. The way it plays into chapter 4 is we'll be presented with a certain type of differential equation that we want to solve. How do we solve it? We'll think of it through chapter 3. So you'll keep revisiting these ideas. If it's any consolation, at some point in the discussion in chapter 4, we'll get to a point where it's just computation. So you'll be able to get back to the process of doing algebra and calculus and solving equations, thinking about oscillations and resonance and all those things. But the explanation for why do we do it this way, why does that work, will rest on this foundation of chapter 3. Okay. So let's get to it. Another new term, kernel. And I don't know the origin of this word, or if I did, I've forgotten. So this section is going to set up sections 4.1, 4.2, and 4.3, which are all homogeneous equations. A kernel of a linear transformation is all the vectors that go to 0. So you have some linear transformation t that goes from u to v, and all the vectors u in the domain that end up going to 0, that's the kernel of t. So think of them as the zeros of the function, the x-intercepts, if you will. They're not that, but that's a pretty good analogy. So the kernel of a linear transformation are all the vectors that are sent to the 0 vector. So let's connect this to derivatives. So capital D, that's our derivative, the linear operator on f. Take a function in f and operate with d, and ask what sorts of x's, what sorts of functions evaluate to 0. Constant functions. It's a whole class of functions. And constant functions form a vector space. It's just the real number line. Consider another operator, d minus 1. What kinds of functions, x and f, are sent to 0 under this transformation? D minus 1 on x equals 0. So, in other words, what's in the kernel of d minus 1? Well, in the previous video, we went over this type of equation. This type of equation gives exponentials. And this is just e to the t. So every multiple of e to the t is in the kernel of d minus 1. That forms a vector space. It's a one-dimensional vector space. There's only one element, e to the t. The basis is just e to the t, and it's every multiple of that function. So solutions to differential equations are related to the stuff in the kernel of a differential operator. I mean, if nothing else, that sounds pretty fancy. So, theorem. We're not really going to prove it, we'll just chat about it. So let T be a linear transformation from u to v. The kernel is a subspace of u. The kernel is always going to be a vector space, in particular a subspace. The 0 is definitely in the kernel by linearity. Any sums in there, right? If u is in the kernel, so it evaluates to 0, and if v is in the kernel, it evaluates to 0, then t of u plus v, well, that's just t of u plus t of v, 0 plus 0. If u is in there 4 times u's in there because you can factor the 4 out. You can go through and check all the pieces, all the requirements of a vector space, and they're all satisfied by the kernel. So, again, who cares? Sounds distinctly mathy. I'll try to contain my glee because I find this stuff really, really quite fun. The kernel of T is a subspace, so it has a basis. If we know the basis for the kernel, we can write anything in the kernel as a linear combination. And this connects right back to differential equations, in particular homogeneous differential equations. And even when they're non-homogeneous, we'll use this as a lens to set up a solution. So take a differential equation like x double prime plus 3x prime plus 2x equals 0. Right? So this can be thought of, we did this before, as 2 derivatives plus 3 times 1 derivative plus 2 times x equals 0. That means x is in the kernel of this operator. It'll turn out that the dimension of this kernel is 2. It's a 2-dimensional vector space because we can factor it into 2 operators, each of which have a 1-dimensional vector space. So we're only going to need to find 2 linearly independent functions that form a basis of this kernel. The solution to this differential equation is something in the kernel. If I have a basis for the kernel, I can write down all the solutions. Did I do that? Yeah, right here. All right, so this top is repeated. So for example, I could factor this into these 2 pieces, and we'll spend more time on this process in chapter 4. And we can find 2 functions in the kernel right away, e to the minus 2t and e to the minus t. They are linearly independent. Why? Because there's absolutely no way of writing e to the minus 2t as a number times e to the minus t. There's no linear combination that writes one as the other. They're not multiples of each other. So they're linearly independent, meaning that, whoops, typo, any function in the kernel of this operator can be written as a linear combination of those 2. So on the one hand, x of t equals these 2 things looks like we're adding exponential functions. This is also the same, it's completely identical. And now notice this stuff, this is completely identical to taking a velocity vector and decomposing it into the velocity in the x direction times I hat plus the velocity in the y direction times j hat. They are the same thing mathematically. E to the minus 2t and e to the minus t are basis elements, and then these c1 and c2 are the components of x in that basis. Now I recognize that conceptually that's a lot to swallow, but that's what's going on here. So we're going to turn a calculus problem into a linear algebra problem, and it will end up making it easier. And we'll develop some rules. You won't always have to think overly about subspaces and kernels. Again, we're using this stuff to motivate what will be computations. All right, so the punchline, and I would argue the punchline of the entirety of chapter 3, is that solving linear homogeneous differential equations, L is an operator, on x equals 0, amount to finding a basis for the kernel. And that won't actually be that bad, although I'm sure it seems awful now. And that's it.